Welcome to lecture 25 of Introduction to Quantum Field Theory. In this lecture, I will continue the discussion of symmetry and conserved quantities that I started in lecture 23. In the last lecture, we discussed how symmetries give rise to conserved quantities in the quantum field theory. Particularly, we found that a classical conservation law in quantum field theory turns into the conservation of the expectation value of the operator corresponding to the classical current. Particularly, we showed that we get such a conservation law from the symmetry E phi goes to E I alpha phi for a complex scalar field. This lecture, I wanted to continue the discussion in quantum field theory and derive additional constraints that correspond to these symmetries that are called ward identities. So the aim for the present lecture is to derive these ward identities, which are additional constraints for correlation function in quantum field theory. A different name or additional name is ward identities or ward Takahashi identities for these constraints. Let us now derive an example of one of these ward identities. So instead of the partition function, I want to consider the expectation value of a two-point function. If you want a full propagator, phi of x, phi star of y, that in the path integral representation is given as the path integral e to the IAS times phi of x, phi star of y. If we just relabel the fields, phi goes to phi prime, without actually doing any transformations, we find that these two expressions have to be the same because they correspond to the same object. However, if we look at the local transformation, phi goes to e to the I alpha of x, phi of x, then for small alpha, we can expand this product of these two transformed function here, such that we get the primed quantities is equal to the unprimed quantities, and we get a 1 from expanding the exponentials of both of these quantities, plus I alpha of x for the first term, minus I alpha of y from the second term. If we follow exactly the same steps as in the last lecture, we find that the conservation or the symmetry in the quantum field theory then gives rise to an expectation value that corresponds to the original object, in this case the two-point function, times the variation of the action, that's 1 plus I integral over z j mu d mu alpha of z. That's the same as in equation 24.14 in the last lecture. And then the variation of the primed fields, which is just the result written in the equation 25.5 here, and the whole thing minus 1 from the transformation, or minus 1 from the original expectation value. If we expand in alpha small, we then get 0 is an integral over phi of x, phi star of y, j mu d mu alpha of z, plus the expectation value of this operator we are considering times alpha of x for the first term and minus alpha of y for the second term. Note that this derivative here acts purely on z. We can rewrite these terms here to more closely resemble the integration that is in the first term. And to do so, we just write alpha of x as an integral over z times alpha of z times a delta function, so that the integration of the delta function will just give us back alpha of x. And we do that for the first term as well as for the second term, where for the second term, the delta function is delta of y minus c instead of x minus c. So doing that, we find that we have an integral over all of the terms, but we have delta functions for the second terms. And then in addition, for the first term, we do an integration by parts so that we get a total derivative which vanishes, and then alpha of z d mu acting on all of the rest of the terms. So we get alpha of z minus d mu of the expectation value of this object here, where again the d mu here acts only on the coordinate z. Similarly to what we discussed in lecture 24, alpha of z is arbitrary. We expand it in a complete basis with arbitrary coefficients. Since the integration over these arbitrary coefficients has to be 0 for all choices of them, the only possibilities is that the integrand, the term in the brackets here, must vanish. And that's basically the result that we get. So we find a Ward identity, which says that the expression in the brackets has to vanish, and that just can be written as the derivative of this correlation function, phi of x, phi star of y, j mu of z. And the full theory is given as the difference between the expectation value of these two-point functions. This is a Ward identity. It basically corresponds to a constraint on some correlation function, this correlation function that we've written down here. If you want to, you can plug in the explicit form of J mu for the complex scalar field. This will involve two terms of phi. So we have the 4-point function, the vertex with 4 entries of the field phi here. And on the right-hand side, we have the propagator, because these are 2-point functions, but the right-hand side will vanish for all values of z, except if z is exactly equal to x, or z is exactly equal to y. So that's what these delta functions here represent. Turns out it is easiest to represent this Ward identity in momentum space. So that's what we'll do in the next slides. Translational invariance for the 2-point function means that this combination here must depend only on the difference x minus y. So we can write the full 2-point function as the full 2-point function where we have shifted the arguments in the following way. And we write this expectation value as the full Green's function of the theory, the full propagator. The term that we have in our Ward identity corresponds to g full of x minus y times delta of x minus z for the first term. So if we do a Fourier transform over x, y, and z of this combination, we get the following result. So we get an integral over x, y, and z, but the integral over z, because of the delta function, just says we have to replace every occurrence of z with respect to x. So if the corresponding term was, for instance, e to the minus I kz, we now get e to the minus I kx. So that's the integral over z already done. We can then look at this expression here, and we can shift x goes to x plus y. So we get an argument of the propagator that's just x. So if we do that, then doing x goes to x plus y, we get the dependence on y is qy from the original term plus pk from the shift, and that is acting on g full of x. And we can recognize that the integration over x here is nothing else but the Fourier transform of the propagator. So we get the propagator in Fourier space, evaluated at momenta p plus k. So it's this term here. And the remaining integral over y is an integral over just this exponential. And we can recognize this to be a delta function. So we find that the Fourier transform of this first term on the right-hand side at the Ward identity gives rise to the full propagator in momentum space evaluated at p plus k and a delta function. Now this delta function is nothing else but saying that momentum has to be conserved at these 3 points x, y, and z. So the total momentum coming in must be equal to the total momentum coming out. So we find that Fourier transforming the right-hand side of the Ward identity gives us the full propagator in momentum space and an overall delta function corresponding to momentum conservation. Momentum conservation must also be true on the left-hand side of the Ward identity. So if we Fourier transform that, we must also get a delta function that is of the same form as the one that we just wrote down. So we find that if we just don't write the delta function because it's the same on the left and the right-hand side, the Fourier transform of the Ward identity will give us something that left-hand side is equal to the full propagator evaluated at momentum p plus k minus the full propagator evaluated at momentum p. We can put in a little bit more work to figure out that the left-hand side corresponds to effectively the full 3 vertex of the theory. So we could work this out in more detail. We will not do this in this present lecture here because the complex scalar field is not realized in nature, so we really sort of don't want to sort of put too much effort into this word identity. But I want to just mention that a similar calculation can be done for quantum electrodynamics, QED, where we also find that we have the 3 vertex on the left-hand side. The main point is that the word identities give us relations between full correlation functions of the theory. For the complex scalar field, the word identity that we derived is a relation between the full propagators, difference between 2 full propagators on the right-hand side, and the full 3 vertex. These are relations of the full correlation functions, and as such, they are not perturbative expansions. We have never talked about small expansions in the small coupling parameter, so these are basically expansions that are, these are results that are exact relations in quantum field theory. So that's different from what we've said before when we were talking about interacting quantum field theories. We said that in many cases, all we can do is approximate results into quantum field theory, where we expand, Taylor expand the exponential intercoupling parameter. Word identities is an exception to this statement. Word identities are exact relations in the quantum field theory, and these are sort of obviously very useful to constrain or derive properties that we get in nature, basically. And this concludes the present lecture.